In this video, I'm going to talk about how I discuss length of daylight. We're given this intro talking about noticing how the length of day is a little bit longer in summer, a little bit shorter in winter. We're also given 4 cities that we're going to be comparing: Houston, Philadelphia, Winnipeg in Canada, and then Porto Alegre in Brazil. The data in all the tables that we're given is from the year 2009, and it's based on the assumptions that the length of daylight is defined as the amount of time elapsed between sunrise and sunset, and because 2009 is not a leap year, there are 365 days. So when we scroll in through this Dana Center activity sheet, we're going to start to see some of the charts that we're going to be using. Here's the chart for the Houston data. Notice it gives you the date, day number, hours, minutes, form, and minutes in length of daylight. Here you're going to see the next chart we have is Philadelphia. Again, same information except just the minutes is going to be different, the hours, minutes, length of daylight. So whenever you graph this, you want to make sure the day number and the minutes are the items going into the calculator. And this situation is a lot like the Ferris wheels, except now we're looking at sinusoidal regression. So when we go to our calculator, open a new document, we're going to go to a list and spreadsheet and enter the day number and the minutes in that list and spreadsheet in order to calculate our sinusoidal regression. So once you get all the data in the X column and Y column, you want to make sure then that you go into menu, statistics, stat calculations, and then scroll all the way down to sinusoidal regression. So when you get your sinusoidal regression, you start to see that we have several decimals or several decimal places given to us in each one of these approximated variables for A, B, C, and D. My recommendation is that you keep as many as you possibly can because it's going to make the equations more accurate, and it's going to make the intersections of graphs that you're trying to compare more closely related as well. So I go 4 to 5 decimals for the B variable, and I go all 3 variables for A and D, and then 4 or 5 for C as well. And that's going to give us a good, very close approximation for all the day numbers and minutes we're trying to calculate whenever we graph. So when we go to our graph, we start inputting the equation. Our A is 113.257. Sine is 0.0168x minus 1.3189 plus 727.373. Now if you remember our minutes, they were in the 600s, and our year is from 0 to 365, so we need to change our window to accommodate those numbers. You can see the maximum and the minimum really clearly with the window that we've established, and then we need to analyze the minimum, maximum of this graph. There you see the the maximum is 172 for its day number, 841 minutes. The minimum is going to be over on the right hand side. Notice also I've done the range a little different. I did it backwards. It still worked. 359 is the day number and 614 is the minutes for the length of day. From here we need something to compare to, so I've gone ahead and calculated the sinusoidal regression for the city of Philadelphia, and we get 168.438 for A, 0.016638 for B, negative 1.29149 for C, and 726.061 for D. And so we want to go back into the graph that we just created and graph a new equation or a new function. So we put in the function for Philadelphia, and again 3 decimals, all the decimals for A and D, 4 to 5 for B and C, and you'll notice they're very close to the graph for Houston. Then when we graph it, it gives us a different color, nicely visible on this calculator. And then we need to calculate maximums and minimums again, as well as now in this case we need to calculate the intersection. And the intersection, whenever we calculate it, it's going to give us basically the time of the year when the daylight is equivalent to the city of Houston. And we have two intersections. The reason why we have two intersections is typically because fall and spring are the times of year when these occur. From this point, we need to be able to convert the day number to a date and the minutes to the hours minutes format. So first thing we need to do is find the day number closest but not more than the day number that we're trying to convert. So in this case 172 is what's trying to be converted, or what's needing to be converted, and the day number closest to that is 152. 182 is technically closer, but it goes over. So 152 is the closest without going over. So then we need to subtract these two day numbers. 172 minus 152 is 20 days. And then let's take that reference of 152, which is the day number for June 1st, and add 20 to it. So 172 is June 21st. And then you need to make sure your students are able to convert hours, minutes from just a total minutes format. So you're going to divide the total minutes by 60, giving us 14.9, meaning there's 14 hours in this minutes total. Then you need to multiply the decimal portion of 0.9 by 60. And 60 times 0.9 is equal to 54 minutes. So the hours minutes format of 894 minutes is 14 hours, 54 minutes. And then the last thing we do is we put this into a chart similar to what the Dana Center gives you. I've created this chart, but I wanted to focus on the comparisons to the Ferris wheel assignment, where we have the amplitude, axis, period, length, and phase shift, and we have the equation. In this case also we have the date and the length of day for the maximum, minimum, and then just that first intersection, and that is length of daylight.